Hello, this is Mrs. Nearing, and we're going to go over a couple examples of how to find the pH of a weak acid or a weak base. So this problem right here, calculate the pH of 2 molar nitrous acid, and the Ka is given. So when you're doing this type of problem, first thing you want to do is write out the equation for the reaction which is occurring. So your acid is a hydrogen donor. So it is going to give a hydrogen to water. That leaves behind the NO2 minus ion, and that generates H3O plus ions. So that is our reaction. We can write a K expression for this reaction, and K expression, this is a Kc expression, so we're using brackets to represent the concentration and molarity, and then we put its products over reactants, and we leave out water because water is a liquid, and we leave out liquids and solids. And since this is an acid, we call this Kc expression a Ka. So Ka is just an example of a type of Kc expression. And we know the value of Ka, and we're asked to find the pH. And the way that we find the pH is by taking the negative log of the hydrogen ion concentration. So that is what we're really trying to find here. And other thing we should note is that hydrogen and hydronium are sometimes used interchangeably. So the pH is the negative log of the hydrogen concentration. You can also think of it as being the negative log of the H3O plus concentration. So really what we're trying to figure out in this problem is what is the concentration of H3O plus. So this is the value right here that we are really interested in. That determines the pH of the solution. So since it's equilibrium and we want to do a calculation involving equilibrium, I can always use an ice chart to organize my information. So in my ice chart, I'm going to ignore water because it's a liquid. I leave liquids out of my K expression, so we ignore them in our ice chart. And if we look at what we're given right here, we're given a concentration of the nitrous acid. That is our reactant. So we start out with 2 molar reactant. We're going to assume we start with no product to begin with because nothing else is mentioned. We're going to use up some reactant. So it's a negative change on the left. We're going to make some product, so it's a positive change over here. It's a 1 to 1 to 1 mole ratio. Equilibrium is 2 minus x. This one is x. This one over here is x. So now let's take these values and plug them, substitute numbers into our K expression down here. So we know the value of K is 4 times 10 to the negative 4. And we know that the top is, x times x, so that's x squared. And the bottom is 2 minus x. And so to make this math easier, we have this trick where if K is 3 orders of magnitude smaller than our initial value, then we can assume that 2 minus x is just 2. So x is so much smaller than 2 that difference is insignificant. Okay, so now we're going to plug things in our calculator. So x is going to equal the square root of 4 times 10 to the negative 4th times 2. So I'm actually going to do that in my calculator really quick, so bear with me. Times 2, and take the square root of it. I should end up with 0.028 is my molarity. Then I have to ask myself, what does x represent? Oh yeah, it represents the H plus concentration. And the problem is asking me for the molarity, it's asking me for the pH. So the pH is the negative log of the H plus concentration. So the pH in this case is the negative log of that value of x that we just found. So if I take the log of that, I end up with 1.55. And if that strikes you as weird with my sig figs here, it might seem as though this number has 3 sig figs in it. But the rule is with logs is that with logarithms is basically the numbers to the right of the decimal are the ones that are significant. So this number really has 2 sig figs in it. The number to the left of the decimal is just a placeholder. What do you mean by placeholder? It's kind of like this number right here. It just tells you the order of magnitude. So are we talking about, it being in the hundredths place, the thousandths place, the tens place? That's what this number to the left of the decimal represents. So that doesn't count as one of our significant figures. It's only the ones to the right of the decimal that are significant. Excuse Excuse me. All right, so now let's go look at a base. Let's scroll down to problem 2. You'll notice these weak bases tend to be amines, which are nitrogen-containing compounds, or they tend to be anions. Those are 2 major categories of weak bases. So let's look at problem 2 in the base category. So what I want to do here, same thing I did with acids, I want to write out my equation for the reaction which is occurring. So I've got these bromate ions and liquid water, and bases are hydrogen takers. So BRO minus becomes HBRO, and H2O loses an H, so it just becomes OH, and its charge becomes negative because it loses something positive. I can write a K expression for this because it's equilibrium, and I am going to call this KB since it involves a base, but you should notice that this is really just a KC expression. We're using brackets to represent molarity. And since we're doing a calculation, let's set up an ice chart. Okay, so in my ice chart, I'm going to ignore the liquid water. I'm only going to focus on the things that are aqueous, or if I had some gases, I would include those too. And remember, our goal here is we're trying to find the pH of the solution. And the pH is the negative log of the hydrogen ion concentration. And it looks like, oh wait, I don't have any hydrogen ions here. Well, another thing that I know is that the pH and this thing called the pOH add up to 14. And I know that the pOH is the negative log of the OH concentration. And all of these things are on your equation sheet. You don't have to memorize them. So what that means, if I can figure out the concentration of hydroxide ions in this solution, I can figure out the pOH, and from that I can figure out the pH. So that's what I'm trying to do with a weak base, figure out that hydroxide ion concentration. So let's fill in what we know. We know that it's 0.72 molar bromate ion, and we're going to assume there's no product to begin with because nothing else is mentioned. Some of my reactants are going to get used up. My products are going to be made. I have 0.72 minus X, and this is X, and this is X. So now I've got my ice chart set up. It's just a way to help me organize information. I'm going to plug these values into my K expression that I wrote. So K is 4.0 times 10 to the negative 6th. My products are both represented with X. So X times X is X squared. On the bottom is my reactants, which is 0.72 minus X. And once again, my K value is so small that I can assume that 0.72 minus X is just 0.72. X is so much smaller that that difference is going to be insignificant. So I'm going to rearrange to solve for X. So X is the square root of 4 times 10 to the negative 6th times 0.72. So you can give me a moment while I plug this into my calculator. Times 0.72, and then I'm going to take the square root of it. I should end up with 0.0017 molar. And the key thing to remember is that this is your hydroxide ion concentration. So I'm going to take if I take the negative log of my X value, in this case it will give me not my pH but my pOH. So I'm going to take the negative log of this number and I get 2.77. So the pH, using this relationship right here, which is on your equation sheet, my pH is going to be 14 minus my pOH, which is 11.23. And it's always good to double check your answer to see if it's reasonable. So since this thing that we're talking about here is a base, I would expect my pH to be greater than 7, or I did something really weird here. Same thing with up here in this earlier problem. Since the thing that I added to water was an acid, I would expect my pH to be below 7. So that's a simple way to check to see if your answer is reasonable.